Okay, let's dive right into this explainer and completely demystify how modern structural engineers actually design skyscrapers to survive massive earthquakes. It's kind of wild to think about, but the tops of the tallest skyscrapers can actually sway several feet in the wind and weigh way more during a severe seismic event. When we look up at these towering steel and concrete high-rises, we naturally tend to picture them as rigid, unmoving fortresses, right? We want them to be perfectly stiff. But the reality of how these colossal structures survive the violent, totally unpredictable shaking of an earthquake is far more dynamic and, frankly, far more fascinating than just building something really heavy and rigid. Today, we're going to explore the absolute fundamentals of nonlinear analysis. It's a vital design tool that engineers use to keep us safe when the ground literally gives way beneath us. And to make sense of all of this, we'll be drawing directly from the incredible insights of structural engineering expert Dr. Graham Powell. But before we get into the real nuts and bolts of how these buildings survive all that swaying, let's start by shattering a pretty major myth about structural engineering. Specifically, this assumption of exact mathematical prediction. There's this really common misconception out there that, with enough computing power, we can simulate exactly, down to the very millimeter, how every single beam, column, and bolt is going to twist and bend during an earthquake. But the truth is actually much more humbling. Think about the difference between a highly controlled laboratory experiment and the sheer, chaotic violence of an earthquake. Earthquakes just don't come with a script. Between the immense unpredictability of seismic forces, the duration of the shaking, and the inherent messy uncertainties in real-world building materials, exact prediction is simply off the table. Dr. Graham Powell actually puts it pretty bluntly. Exact prediction of behavior is impossible. Can't be done. And what's really interesting about that admission is that structural analysis is actually about usefulness, not perfect accuracy. As he points out, if you're looking for a crystal ball to give you a perfect, exact simulation, you're just not going to find it. But here's the thing. Engineers don't need a crystal ball. They need a reliable roadmap. The whole goal of modern engineering is to gather useful, actionable information so they can make solid, life-saving design decisions on exactly how a building will ultimately fail. That way, they can control that failure. And to do that, engineers have to move way past simple linear math and embrace a much more complex tool to actually map out that roadmap. Which brings us right to our core concept for today, nonlinear analysis. This is the exact tool engineers use to embrace the messy reality of controlled damage. Let's break this down a bit. In standard linear analysis, you basically assume a building behaves like a perfect spring. Imagine a metal slinky. You pull it a little bit, it stretches, and when you let go, boom, it snaps perfectly right back to its original shape. That is linear behavior. But earthquakes, they absolutely do not care about perfect springs. They apply forces that push structures way, way beyond their elastic limits. Imagine pulling that slinky so far and so hard that the metal permanently bends and warps. It is never going back to its original shape. Nonlinear analysis allows engineers to actually map out what happens in that chaotic zone after a structure starts to permanently deform, yield, and take on damage. And this brilliantly illustrates the two distinct ways a building actually changes under that extreme stress once we cross over into nonlinear territory. First, we have material nonlinearity. The easiest way to think about this is with a simple analogy, bending a metal spoon back and forth. You bend it once, it's fine. But if you bend it rapidly back and forth 10 times, the metal starts to yield, it heats up, it weakens, and it degrades. In a building, this looks like massive concrete columns cracking or steel beams yielding under cyclic earthquake loads. Now, on the flip side, we have geometric nonlinearity. This is when the overall shape of the structure changes so drastically under stress that gravity itself becomes the enemy. Imagine holding a heavy bowling ball straight up above your head. Relatively easy to balance, right? But the second you lean your arms slightly to the side, gravity grabs that heavy ball and suddenly it wants to pull your whole body down to the floor. That's geometric nonlinearity, known in the engineering world as the P-delta effect, where the building sways so far off-center that its own immense weight threatens to topple the whole thing. Now, let's contrast the old way of thinking with the new. Historically, engineers relied really heavily on strength-based design. This is all about staying completely rigid and making sure force demand never ever exceeds force capacity. And look, it's great for static loads like the everyday weight of desks and people. But under a dynamic earthquake, behaving like a perfectly stiff, brittle glass window that just shatters instantly under too much pressure is an absolute disaster. That is exactly why old historical brick buildings often suffer such catastrophic failures during quakes. Instead, modern engineers use deformation-based design. Think of a modern car's crumple zone. A modern car is literally designed to crush safely upon impact, absorbing the kinetic energy of the crash to protect the soft passengers inside. A skyscraper is designed the exact same way, to yield and deform safely to absorb the massive dynamic shockwaves of an earthquake. So why the total shift in approach? Well, the crucial point is that it is simply financially and physically impossible to build an unbreakable, perfectly elastic building that resists an earthquake's full force without ever bending. I mean, if you actually tried to build a skyscraper strong enough to stay perfectly rigid during a major quake, it would basically have to look like a solid windowless pyramid of pure concrete and steel. And frankly, no one wants to rent a corner office in a concrete pyramid, because the elastic force demands of a severe earthquake will almost always exceed the actual strength of a practical, usable building. The building must yield, period. But since earthquake loads are dynamic and incredibly brief, whipping back and forth rather than just being a constant, steady push, exceeding that strength temporarily doesn't mean the building immediately falls down, not as long as it has the engineered ductility to yield safely. To actually manage this, engineers define 3 very specific performance levels for this controlled deformation. First, if we want a building to be fully operational right after a quake, like a hospital for instance, we design for immediate occupancy, allowing almost zero structural damage. If we can accept some substantial damage but want to ensure absolutely no one gets hurt, we design for life safety. And finally, if we're dealing with the absolute maximum credible earthquake, we're talking the big one, we design for collapse prevention. Now, collapse prevention might sound a little scary, but it essentially means the building is totaled. Just like a car after a severe highway crash. The building pushes its absolute ductile limits, it's ruined, and it's probably going to have to be torn down later. But it did its job perfectly because it stayed standing just long enough for everyone inside to walk away safely. And here is where we get to a truly profound realization. Because exact prediction is impossible, engineers realized they have to intentionally pre-select exactly where the damage is going to occur. Think about it. If you just build a stiff frame and wait for a computer analysis, or much worse, a real earthquake, to tell you where it's going to yield and snap, you are leaving human safety entirely up to chaotic chance. You're blindly hoping your math perfectly matches a very messy reality. To guarantee safety, structural engineers have to completely take the decision out of the earthquake's hands. They aren't just reacting to nature anymore. They are dictating the terms of engagement. They decide what breaks, when it breaks, and how it breaks. So how do engineers actually dictate those terms in the real world? They use this brilliant conceptual framework called capacity design, and it operates exactly like the electrical fuse box in your own house. In your home, a cheap $20 fuse is intentionally designed to blow in order to protect your incredibly expensive flat-screen TV from a massive power surge. In a skyscraper, engineers choose specific structural components, like the ends of certain horizontal beams, to act as those intentional fuses. They design those exact parts to be incredibly ductile so they can bend, warp, and absorb massive amounts of energy without snapping. Then they design everything else around them, like the crucial vertical columns supporting the entire weight of the building, to be super strong. That's the expensive TV. This ensures those critical elements remain perfectly elastic and totally undamaged, while the fuses do all the dirty work. By choosing these weak points in advance, engineers basically execute an ingenious hack against the chaos of nature. Instead of just seeing these as a list of benefits, think of them as immense victories over unpredictability. Victory 1. They take back control. They make their nonlinear computer models exponentially more reliable simply because they've already forced the math to yield right where they wanted it to. Victory 2. This allows them to calculate the structural demands on the rest of the building with far greater accuracy. And Victory 3, which is perhaps the most critical of all, it results in a highly forgiving design. If an earthquake hits that is actually much stronger than the building code ever planned for, a building using capacity design is far more likely to behave predictably and stay standing, protecting the lives inside. But look, even with the absolute brilliance of capacity design, assessing a towering structure is insanely complex. A large multi-story frame building might have hundreds of thousands of individual points, known as plastic hinges, that could all be yielding simultaneously during a major quake. Let's be real, no human engineer can look at a massive, chaotic spreadsheet with 100,000 rows of raw yielding data and make a life-or-death safety judgment. So to process this mountain of data, computer programs group these thousands of tiny stress points into logical, summarized sets. They call these limit states. It's basically like taking that impossible 100,000-row spreadsheet and summarizing it into a few easy-to-read charts. For example, grouping all the hinges on the perimeter girders and seeing if they collectively meet that life safety level we talked about. It distills chaotic data into manageable metrics so human engineers can actually make sense of the damage. Okay, so engineers then have to test these models to calculate the exact demands, and they generally use one of 2 main methods to do it. They can use dynamic analysis, which is essentially a brute force computer simulation. It steps through a recorded earthquake 1/100th of a second at a time. It is incredibly accurate, but it demands a massive amount of computing power and time. Or they can use what's called static pushover analysis. This is where the computer slowly pushes static loads against the digital building in one direction until it reaches a target displacement. It's way faster, but remember our spoon analogy from earlier? Real earthquakes whip a building back and forth, right? They degrade it through cyclic motion. A static pushover just pushes it one way, which means it completely lacks that true cyclic motion. This makes it highly approximate, and generally it's just not suitable for very tall or highly complex structures.
But here's the thing. No matter which complex analysis is used, whether it's an advanced dynamic simulation crunching 7 different historical earthquake records for weeks on end, or a quick static pushover, it all boils down to the single absolute golden rule for every single limit state. The demand-capacity ratio must be less than 1. The demand the earthquake places on the structure simply cannot exceed the structure's capacity to handle it, period. And in structural engineering, a ratio of 1.01 isn't just some minor rounding error. It is a failed design. If that ratio creeps even a fraction above 1, the design completely fails the performance check. The engineering team has to go right back to the drawing board, sharpen their pencils, and redesign the building until it is undeniably absolutely safe.
I want to leave you with a final provocative thought to carry with you today. True structural safety isn't about rigid, unbreakable strength. It's just not. It's about a highly choreographed, mathematically simulated dance of yielding, bending, and absorbing energy. It is about knowing exactly how, exactly when, and exactly where a building is going to break to protect the fragile human lives inside. So the next time you look up at a towering high-rise, or hey, even just look around the room you're sitting in right now, ask yourself, where are the structural fuses hidden in the walls around you, just waiting silently to bend so that the building won't break?